Hello everyone, and welcome to the session. So, real-time data engineering decoded. In this session, we are going to explore how the modern data architecture are evolving to handle streaming data and instances analytics without operational bloating and complexity of traditional stacks. So, let's jump into that agenda of the session. So in this session, we are going to see this guide of this agenda. So first, we are going to see the data engineering challenges in the modern analytics, and second, we are going to see the real-time analytics versus traditional batch performance comparison. Next, we can jump into that introduction to VeloDB architecture and key features, and VeloDB storage architectures, as well as the ETL data synchronization and OLAP in VeloDB, and then we'll see the live demonstration and Q&A session. So let's jump into our first agenda, the data engineering challenges in the modern analytics. So in this, let's start the root problem. So the first root problem is that most data pipelines are designed in the overnight batch processing. So due to that, we are not able to get the real-time data from that our model data warehouse. So it's prevent to take the better decision in the business needs. So second thing in that business expectations, we have some fraud detection alert system and personalized now data. So this kind of thing. So in that traditional things, we have our sole data, but we doesn't have that second sole data. So until the next cycle processing, we have only the our sole data. So third one is ADA query, analytic query kind of things we are facing here. So generally in that traditional kind of data warehouse system, so in that ADA query is taking around 1 to 2 minutes to give the result to the user or that MI system, machine learning assets. So due to that, it's taking more time to complete and giving the result to the user. So these kind of mitigations so we can reduce in that modern analytical data warehouse systems. And coming to the injection method, so in the traditional warehouse data analytics system, we have some fixed hours only to inject our new data into our warehouse. So, but in that real-time modern analytics, we can do the continuous synchronization between our source to our destination data warehouses. So that fifth point is computing cost scale unpredictability. So in that traditional batch system, during that our data ingestion process, our resource will be utilized in the peak, and but in between that batch processing window, it should be in the idle state. So due to that, we are allocating some resources to our computing. So it's getting to increase the operational cost also. But in the real-time modern analytics, we can mitigate this kind of economic things in that as well. So coming to in that fragment stack component the problem. So as I said earlier, in that traditional batch system, we have to allocate some separate integration kind of part of things. So first is the data warehouse and the vector databases and search engines as well. So in the data warehouse, we are storing our all data, archive data, and everything in that. So as per that user query or business need, we have to first vectorize their query using our search engine. After that, we have to store that into our vector databases. So here, we are facing some issue to integrate in part like data warehouse into search engine and vector databases kind of thing. So using some modern analyticals, we can go with the one layer up to integrating all part of things. So this kind of issue we can prevent and overcome using the modern analytics. So here I have categorized that fragmented compound problem. The query first is the query latency. So as I said earlier, in that batch system, batch traditional processing, we are facing some ADA query analyticals taking 1 or 2 minutes to complete the process. Second up to few seconds giving the query to that our business intelligence tool or else the machine learning part. So in the same kind of similar workflow. Coming to the injection pattern, so in the batch ETL, typically we are running the fixed schedule of to inject the data from our source to our data warehouse. But in the real time, we have some continuous streaming injection method in that, so that new data queryable within the second without blocking our injection process. Coming to the third thing, concurrency handling. In the traditional system, so it's degrading our response time due to this blocking of our new injection data processing. But in the modern analytics, we can mitigate that issue and we can prevent this kind of concurrency handling as well. So let's jump into our third agenda, the real-time analytics versus traditional batch comparisons. So as I said earlier, I have given the some metrics like query latency, injection frequency, and data freshness, concurrency learning. Real time, so we have some sustained throughput to injecting the data into our warehouse as well as in that getting the result to that BI system as well as. So coming to that last agenda of my side, cost and operational impact in that our real-time analytics is the traditional batch. So here I have given the cost category, compute, storage, and operations. In that batch oriented, the compute cost would be the data injection, my ability to continue data streaming, and as well as the data state processing as well. So the second cost category is the storage part. In the traditional, we doesn't have any compression technique, but here we can able to 70% of reducing the storage layer to store the data into our data warehouse, so that we can overcome this some kind of storage part cost level at Linux as well. Coming to the third one, the operational, we need to in the main warehouse system, but less integration method, so we can easily integrate our data warehouse and vector databases on there elastic searching as well, so that we can follow with the one layer of method to that to build our real-time data analytics system. So I think that's the demo of everything. So let me hand over the session to Shilin.
Good evening, everyone. My name is Shilin. I'm a principal solution architect working for VeloDB. Today, I'm going to share with you the secret sauce of VeloDB, like tell you how does it work, what's the secret sauce, why it's so fast, and hopefully you can find some use case that's suitable for your um, company, right? All right. So a little bit about VeloDB. VeloDB is actually founded by the founding team of Apache Doris, which is the top level Apache software foundation project. It's actually probably one of the most important data warehouse products in Apache software family. The company was founded in 2022 and headquartered in Singapore. The company raised $140 million funding until now. And in Apache Doris community, the company has like one PMC chair and nine PMC member, 26 committers. The GitHub star of the project is around 15,000 stars. Actually, it's 15,800 a few days before I checked, right? And it was being used by more than 5,000 enterprises across the world. Then VeloDB, not only as a company brand, but also as the product brand, because VeloDB I assume it's a database for velocity, right? So it's also the product name, and it's analytical database that is superb at performance. You can do super low latency queries at high QPS. It's a unified real-time database, data warehouse, observability platform, and hybrid search engine, right? And it's super cost efficient. Typically, you'll see 20 to 50% lower TCO compared to competitors, right? And it is AI ready, so you can perform vector search, MCP server integration, and AI SQL functions that embedding all those things are already integrated in. So it's like battery included whenever you open it, and you can use it already. The next, actually, I'm going to tell you VeloDB architecture and secret sauce, what makes VeloDB different, right? So the first thing I want to cover is actually about the data layouts. ValvDB, unlike many traditional data warehouse that you probably used before, Snowflake, Databricks, or Google BigQuery, ValvDB data layout is well managed. So we have a different level of levers we can use to prune data so that whenever you run a query, we can query the data very efficiently, right? The first lever we're going to use is actually called partition pruning, right? This one is not strange, not really new because almost all the data warehouse product they actually support partition pruning, and even BigQuery, Databricks, and Snowflake supports that. To give you more illustration, I will maybe share the case where you have an orders table that contains 1 petabyte of data, which roughly 1,000 terabytes, right? 1 million gigabytes, right? Then you want to get for the specific day, 2026, August 12th, and you want to find a total order amount for user ID 4213, right? So first of all, the query engine will look at, okay, now you look at 1 date or even 2 dates or 3 dates, right? So we know exactly which partition contains the data. We look at the partition only and not the remaining of the partition, right? So by this condition alone, we can reduce the scan size from 1 petabyte to 2.7 terabytes, right? Then we look at the user ID because we can distribute the data based on the hash of the user ID, right? So look at user ID is 4213. We use this to calculate the hash. I use this to divide by 128. We get a remainder of 117. 117 means that if the user has any data at all, then it must be in bucket 117, right? So we only need to look at bucket 117 only. Instead of 2.7 terabytes, we only need to look at 21 gigabytes of data, right? Then within this bucket, right, the data is actually maintained in a sorted order, right, based on the key that you have. So you can see here the user ID and order time is sorted, perfectly sorted. That means the user's data is perfectly continuous in this data layout. We need to do a binary search. Then we located the starting of 4213. We scan the rows until we reach a different user ID. Then we know that the sum is completed, right? So you got these 3 data points and you do the sum. The answer is 97.99. So instead of scanning 1 petabytes, we scan 3 rows out of 42 million rows, right? And at most a few megabytes I/O only, and you probably get a query done in within 10 milliseconds or 5 milliseconds. So you can see this pruning is really efficient. We reduce the row scan from 2 trillion to roughly 5.4 billion to 42 million to 3 rows, right? So shows the power of the efficient engine. And if you do this in BigQuery, probably you can get the result probably in 3 or 5 seconds. Doesn't matter. 3 or 5 seconds is already 1,000 times slower than what ValvDB is going to offer. And you pay a lot of money for scanning because you activate thousands of the cores and they work you for 3 seconds, right? That's still going to cost you a lot of money. The next thing about is actually the underlying storage architecture, right? So ValvDB is fundamentally is 3 tier of caching. So the source of truth is always on the S3 buckets, right? S3 bucket offers you a few things. First of all, it is super cheap, right? You only pay like 2 point something cents per GB per month. And we can even apply compression on top of it, so you pay even less. The second one is actually the beauty of it is actually you don't need to store 3 copies, right? Many analytical database says, oh, I store 3 copies, like Elastic, MongoDB, they store 3 copies, and you're going to pay a premium of SSD, and also you store 3 copies as well. And S3 we don't have to, right? On top of that, we can build a disk cache layer. That means the objects, right? If we need them to be on disk, we can fetch them over to disk, store them until we don't need them anymore, right? Then from the disk, we have the Linux kernel page cache. You can store the data in a hot accessible manner. And on top of that, we have memtable stores the data, so we can fast access them. So I give you 3 cases where you run the same query we discussed just now on the code query. It may take 200 milliseconds, right? Because whenever you hit this, we realize, oh, data is not here. Let's fetch this from S3, right? We fetch a few megabytes, 3 or 5 megabytes. Each of them take like 70, 80 milliseconds, right? And then we feed them in the page cache and we go to the query engine and you get result in 200 milliseconds, right? Then before the cache going to be evicted, you run the query on the same data set again, they will be returning to you in 5 milliseconds, right? Because the disk already has the cache, we don't need to fetch from the S3, and the local access is super fast, right? It's called warm query. There's also a hot query. Basically, you just request this query 25 seconds ago, and the data is still in memory, right? We can service you with from the page cache as well, right? So within 1 millisecond, we can answer the query. So most of the customer-facing analytics, they'll see a cache hit ratio of more than 99%, and the P99 return time for query typically sub 100 millisecond, right? So that's what makes so fast. Another thing that I think is super important is actually VeloDB supports indexes on top of the data. So just now I talked to you about data storage layout, which already covers the partition pruning, bucket pruning, and also the binary search based on the key you used, right? But sometimes you just need to query on something that not really the primary key. There are some other keys you want to query from. In this example, assuming you have orders, each order has a address, for example, and in this case, we need to find orders that near certain train station, for example, right? So this is the power that we can use the ValvDB indexes to accelerate the query, right? So in this example, we're going to look into some specific order table with 1 petabytes data points again, right? So this is again is around 2 trillion rows, right? So what we need to do is that, okay, we need to look at, for that particular date and for the orders, right, which is placed near a specific location on the map within 500 meters. How do we do that, right? First of all, you can see that the date is actually a key hint about the partition pruning. Same, from 1 petabyte, we can reduce the scan range to 2.7 terabytes, right? Now, because this is not really hash bucket based on the geolocation, right? So we don't really know which bucket we are going to scan from. So the bucket pruning is not applicable. But thanks to this index feature ValvDB offering, right? So this Geo6 encoding actually be able to partition the whole map into many cells of 1.2 km wide and 0.6 km high cells, right? Each cell has a unique 6-character encoding, right? For example, in this example, our place, the train station is actually located in the cell W21Z71. And thanks to GeoHash 6 encoding, and all the 8 cells next to this cell is encoded as a predictable cell name. Like for example, the one above it will be W21Z74. The one below it should be W21Z70, for example, right? So in this case, we know that that cell is wide enough, and we know whenever we need to look for 500 meters around that cell, we just need to look at these 9 cells altogether, right? So we just need to ask ValvDB, hey, can you get me all the entries that have Geo6 in these 9 cells? And because we have this inverted index, right? So with each cell, we can exactly know that which row in the table has that value, right? So for example, W21Z72, we have R7, row 7, row 91, row 203, blah, 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 right? So in this case, we can go to the buckets and fetch these rows, right? Assuming this 128 tablets open, it's very cheap. We can go there and scan roughly 200,000 candidates, right? They are all within these 9 cells. But instead of the 5.4 billion rows, right? We don't scan them. We scan only 200,000 rows and only roughly 100 megabytes touched. And this is still pruning more than 99.9% of the data off from this huge data set, right? So after that, we can apply the further distance criteria. I mean, not every rows returned will mean that they are near this position within 500 meters. So we can use the additional distance function, right? All the records you return from the cell, we just need to calculate the distance, right? Now we find exactly, like, for example, 5 points, 5 orders that near this location. So You can think that as instead of scanning 1 petabyte, we actually end up scanning maybe 100 megabytes, and we will be able to return the data within like 50, 100 millisecond, right? So this is super efficient query. Okay. There are other stuff that is really helping ValvDB to further accelerating the query, right? One is actually the columnar storage. So typically, database row stores the row in the row format. Whenever you want to do an I/O, you want to select, for example, you want to select the date and the amount. They will read all the rows out. If you have 40 columns, you will read 100 GB. Then if you just select in the columnar database, right, you select date and amount, they will only read these 2 columns. This could be just 5 GB out of 100 GB, which is only 5% of the I/O required, right? And because the data is actually co-located in the columnar store, you can compress them. For example, there will be continuous date of the same value, right? So instead storing 100,000 this value, we can store one value and say repeat 100,000 times, right? We only store one entry. This is the core idea of compression. So because of this, we do less I/O and we store cheaper and we can read faster. The second one I will say is vectorized execution. This actually is using the technology called SIMD. I'm not sure you have heard of it before. It's actually single instruction multi-data point, right? Imagine you want to add all the amounts, taking a look at the same query. Let's say you want to add all the amounts together, right? You have like 4,096 rows you need to add, right? So even if you write the same code, right, they will do a for loop on the many value. For each of them, they will check whether it's done or not. If it's not done, then add the sum, then jump, right? So this is roughly, let's say for 16 value add, you will use 48 instruction because of the assembly, right? Then using SIMD, you can just do a v-add ps. PS means a single precision, right? You just pass in the vector address, and they will add this all the 16 data points using one CPU instruction. There's no comparison, there's no jump. One instruction, the sum is already calculated. So you can see easily like 10 times faster query execution, right? Then the next one is actually massive parallel processing, MPP engine. Doris is built on top of C++ with the MPP engine. That means you run a query. The query will say, oh, okay, this you need to run scan 450 megabytes data, right? And the B will be slicing the data workload. And assuming you have a 10 BE backend, then they will just take one shard each and start scanning in parallel. Once they have the data, they merge data at the upper level and give you the result, right? So the parallelism will save a lot of cost. Then the last one is the cost-based optimizer, CBO. CBO is actually an intelligent engine so for example, sometimes you can use pruning, sometimes you can use index, but what's the best way, right? We may look at the cardinality or the effectiveness of the filtering condition. Plan A says join everything, then filter. Plan B says filter first, then broadcast smaller table. Obviously, plan B will be broadcasting only 6 million rows, right? Will be 300 times less data to be scanned and joined, right? So CPU will choose plan B to execute it, right? So it's very intelligent query system. If you look at this, again, columnar I/O will reduce this I/O significantly. On the 40 column table, on 2 column select, you will use 20 times less I/O. SIMD easily bring 10x performance compared to your traditional Java or C++ based for loop and query engine. MPP can activate 10x of the nodes in shorter time to scan more data. You can achieve the same result with much less time. And CBO can be yet another 100 times scalar on how to execute the query in the cheapest possible fashion, right? In this, you can do petabytes of data scanning in sub-seconds. Okay, so on top of that, VeloDB is often used as a data warehouse, but sometimes also used as a lakehouse, right? The difference between the data warehouse and lakehouse is actually VeloDB support internal data format, which all the features I mentioned earlier, like the indexes, partition pruning, hash bucketing, they are all supported in the internal table. And the internal table is cheap as well. It's backed by S3 buckets, right? We also support lakehouse format where you can use iceberg or Pymon formats on top of S3 as well, right? So they work differently, like partitioning. I mean, partitioning is okay for VeloDB as well as the lakehouse, just that the lakehouse partition layout is actually fixed for you. You cannot choose, right? Hash bucketing, no, we have the hash bucketing. Lakehouse doesn't have it. Invert index, we have it. Bloom filter, we have it. Zone map, prefix index, we have them. And the lakehouse doesn't have it, right? The prune everything, right? By anything, very heavy pruning, we have it, and the lakehouse doesn't have it. Background compaction for data organization, organize data in the right format, we have it. The lakehouse doesn't have it. But we are open platform, right? We don't really force you to choose the internal data table, although it has so many advantages. But some customers still want to use lakehouse using Iceberg, right? Um, that's actually possible, right? So if you use lakehouse, right? Lakehouse typically backed by S3 or object storage, the same, but all the other benefits I mentioned earlier, the three-tier cache, the vectorized same-D execution, they are still applicable, right? So on top of lakehouse, typically user will say, I will use materialized view to materialized view is the table stored within VeloDB internal table format, but then you can do the calculation once, right? So if you use lakehouse, you probably will be doing like, okay, every end of the day, I will update my iceberg with the new partition for yesterday data, right? Then for yesterday, I need to calculate revenue by user, revenue by product, revenue by hour. All this can be done by a materialized view. They are pre-calculated once on ValvDB, and materialized view is refreshed. Then all the dashboard on the stale data, they never need to come back to Iceberg ever again, right? Instead of querying 2 terabytes slow S3, you query on cached materialized view on internal table, right? Maybe it's only 500 megabytes, right? All the query are blazing fast, and you can service a dashboard in the blink of an eye, right? You can still enjoy your benefits I mentioned earlier, like MV, material view, typical query will take less than 100 milliseconds. Repeated query on S3 will be fast as well because we cached the local NVMe disk already, right? And the first code query is slow because it may come from the S3 directly. That will take the S3 to disk backfill, but you still enjoy the MPP engine and the vectorized execution result, right? You can still see a huge performance boost compared to Trino or any other um, lakehouse architecture analytical platform. Okay, then I will talk a little bit about using ValvDB in practice, practical scenario, right? So in the real life enterprise, you may have data coming from relational database, lakehouse, data lake files, Kafka, for applications, right? So for RDBMS, we have CDC. You can use CDC or Flink or routine load to read from database and write to ValvDB in almost real time. For lakehouse, or Parquet files, you can use broker load to load into the VeloDB. And Kafka, we can use routine load with some ETL processing. You can go to VeloDB very easily. And application you want to write in real time, you can also use the stream load or JDBC insertion to insert data into VeloDB, right? On the consumer side, you will have your typical application that using JDBC or MySQL protocol because ValvDB speaks MySQL wire protocol. So it's binary compatible. So you can use them to connect to ValvDB and start issuing query and get results, right? And if you have a requirement to read data from ValvDB using hyper speed fast SQL, you can also use Aerofly SQL. Aerofly SQL allow you to read the data from ValvDB in tens of gigabits per second, right? In the test recently, we achieved around 70 plus gigabits per second reading from ValvDB using SQL. And this is how our Flink connector and the Spark connector read data out of VeloDB as well, right? Other BI tools, visualization tool, you can use MySQL compatible protocol to connect to VeloDB directly. Okay. With this, I will do a quick demo for you, and that will show you the practical practical use case that you have in your enterprise, right? So I'm going to stop the presentation mode and go to my browser, right? So here, here we built a very simple website to simulate e-commerce, right? So this is very close to the slide I explained a little bit earlier, right? So here, this application is a Go application that simulates the e-commerce portal. It is backed by a Postgres SQL database, and using our CDC engine, we are reading from Postgres directly, then ingesting to ValvDB Cloud using a four-core machine, the tiny machine, right? And then on top of that, we're using Materials View to pre-calculate some of the metrics I'm going to demonstrate. Then using this ValvDB, we can empower this ops support, BI dashboard, and AI agent, right? I'm not really showing AI agent, but actually you can use AI agent or MCP server very easily. Okay, so the portal has a Postgres side, right? So we have a data generation, right? So we are generating data like, okay, for example, for user events, product events, order events, shipments events, we are generating at a certain speed. I can adjust the QPS and start and resume, pause or resume the data generation as well. So this basically to keep the Postgres alive, right? Postgres keep have data coming out. Later I want to show you how does the data go to Doris or VeloDB in real time, right? Okay, so products, orders is the main table we're looking at. Orders is actually coming up in real time, right? Now from typically, if you want to build a dashboard on top of Postgres, whenever the QPS goes up, right, your Postgres will struggle because they will be busy handling a lot of requests already, right? They cannot do this analytical query. So in ValidDB dashboard, right, you can actually see here, right? Here is actually you can see the per minute revenue, right? So every minute, this is 7:10, 7:09 p.m., 7:08. Every minute we have a revenue. You can see here the revenue is actually now we just crossed 11, right? 11 already see revenue, 27 orders come. So you see the revenue is actually coming here in real time, right? Whenever order happens, because this is powered by ValidDB, transaction happen in the Postgres, they will be synchronized to ValidDB in real time, and we can calculate the per minute revenue in real time, right? Here you can also see the top products, right? And these are all calculated in real time, except for for example, let's say you can see that the past few minutes, right? The past time, the data is pre-calculated already because there's no data coming in, and the materials view already have the data. Only the last minute data is calculated in real time. The others are all calculated like in the materials view, so the query is super fast, right? Now, I want to show you something is like in OLTP data may be mutating. Let me show, okay, let's say I'm generating orders of like 10 events per second, right? Let's do 100, apply. So now I'm generating 100 events per second, right? And let's go to the ValidDB dashboard and see what happens. You can see the revenue will go up. See revenue already see a hockey stick. Revenue already go up. This shows that whenever you adjust the TPS, the dashboard will just simply reflect it immediately, right? So this actually shows that, okay, everything done is actually in real time, not the fake data, right? Why I say it's actually it's supporting your operational is because that then assuming you have a user ID 12, right? Let's go to valid. They have a query. You can go to this page query user 12. User 12 is me, right? And the username is 44444. And I can make some changes to it, right? So that they can show up here. So let me change something about user. Uh, I can change the demo, email, everything I changed. City, I changed New York, right? and the country I set to United US, right? Whatever. I just push save, right? So because CDC is running here, right? So if I come here and search for user 12 again, imagine this is coming from VeloDB, right? You can see the query taken. The query take time 20 milliseconds. It's almost as good as you know MySQL local query. And you can see my name has been changed to demo. My country is US and the city is New York already. That means ValvDB maintain a super low latency. It's a real-time database, and you can trust trust it as a source of truth, right? Whenever user call your call center, hey, something about my order. What's your order ID? You can trust this is already up to date. You come here and look for the order ID user is looking for, and data is already up to date, and it takes 19 milliseconds. Imagine how fast it take for you to query a row from Databricks or Snowflake, right? Easily a few seconds, and that's a lot slower not only, but also pay a lot of money. Okay, so this actually shows that a few things. The CDC with VeloDB is really, really simple, and the latency is really, really low, and all the dashboard calculation, they are really, really efficient, right? You can see my revenue just like skyrocketed because I have more orders, right? Okay, so that's my demo. Let me go back to my presentation. Okay, so just to want to recap the ValvDB, if you want to try ValvDB, how do you get started, right? So ValvDB offer three different deployment models. One is the ValvDB Cloud, right? You can run SaaS, zero ops experience, just like how do you use BigQuery or RDS, right? Just go and create, then start spamming ValvDB on the cloud. We also support bring your own cloud. Basically, you can run VeloDB with your AWS account or GCP account or Azure account, and everything storage compute is in your VPC, right? We can also run self-hosted on-prem VeloDB Enterprise, right? This is suitable for companies that cannot move the cloud for whatever reason. You want total data locality and you do not want to use cloud, then Enterprise is the way to go. So all the three, choose any of them that suits your purpose, right? Okay, so that's my presentation for today, right? I will stop here, answer any question. Arun will answer a question as well. If you want to try VeloDB Cloud, you can use the QR code. And if you want to join the VeloDB community, we have a nice community managers supporting users, even you are using open source, right? Your support. Shirley will be supporting you a lot. And we have technical engineers on the channel on duty to support you for any question you have.